first demo is going to be focused on topology optimization and convergent modeling. Okay, so just to give you a heads up, so this is what the platform of SimCenter 3D looks like. So typically the way SimCenter 3D works, or NX, so they're both, essentially called, the same name for the same product, is we have a part environment or a CAD environment in which you import geometries from other tools like SolidWorks or PTC Creo, tools where import functionalities that allows you to import natively these kind of files without having to go through neutral files, translation.
Can you import SolidWorks files into NX?
Yes. So you won't get the history tree because that's only on the specific software.
Yeah.
However, they will come in natively without having to go through a translation process. So you won't lose any of the feature, if you'd like. And then you can use from there, our convergent modeling capabilities or our synchronous tool capabilities to make those changes dynamically. And I'll show some of that later on. Once you're done with the CAD, what you do create afterwards is what we call a FEM. So that's essentially the mesh. Okay. Now, what's nice about SimCenter 3D or NX is that the mesh is associatively tied to the geometry. So if someone somewhere creates a design change of that geometry, you can push that modifications all the way to the FEM, which will update the meshes, which will update your bolted connections. You have some of them automatically. Okay, so they're all tied together. So right now, by the way, all of the discussion I'm having right now is outside of a Teamcenter environment, but everything I say also applies to a managed environment. All right. So this is the FEM I've been speaking about. All right, and I'll go to the simulation part afterwards, where I define the boundary conditions and the loads in just a moment. But in this case, the objective I have is to use topology optimization to design a space bracket. Okay. So this is my volume, my control volume. Okay. So if I hide the mesh here, just show kind of the geometry. So this is the volume within which I need my bracket to stay within. All right. Now that bracket is going to be exposed to a variety of structural loads, which I'll define in just a moment, but also a variety of functional requirements when it comes to structural connections. Okay, and what are those? So if I just go ahead here and show the points, you'll see that in space, you see the little crosses. These are my locations of connections. So I want my software, I want to tell the analysis, I will want to have bolted connections in that area. Okay. So what we can do is, instead of creating those connections manually, use what we call selection recipes to give an intent, a functional intent to my model. So what does that mean? So if I go down here and look at my selection recipes, okay, so you see selection recipe A, what I'm essentially telling that area, which is the point, is select all of the nodes. So, by the way, are you guys familiar with structural connections? Yes. Yeah, excellent. All right. So select all of the nodes within a sphere of 4 millimeters to apply that structural connection. Okay. So that avoids the problem of having to recreate a connection every time you refine your mesh. Okay. So that's very important in the topology optimization, because you're constantly refining the mesh and resolving the software, modifying the geometry. So you don't always know what's going to be in that location. Okay, so this is kind of a nice tool or functionality that's in the software, and that's similar to what Joe Luxmore presented when he introduced templates for automatic meshing. Okay, so this is essentially it. So it's called selection recipes. Okay, so at this point, there's no mentions of the actual connection. That's just a functional pointer. Right? So pick all of the nodes within a certain sphere. But what we can create afterward is what we call universal connections. Okay. So universal connections is again a functional way of creating connections without even having a mesh. Okay. So you only define a connection that's when we do bolted connections, what we do is we pick typically a point that's going to be my master or my center of my bolt. And then what we do is we project those spiders as rigid elements to the surrounding model, and create those rigid elements to simulate or mimic that connection, right? But because the mesh is not created yet, it's just there, right? How can you define this? Well, you do so by specifying that selection recipe. So what I've just done in 2 clicks is create a bolted connection with, at this particular point, using all the elements within a radius of 4 millimeters. Okay, so it could have been a sphere, could have been a cylinder. You know, the shape of that hole can be, you know, whatever you want, essentially, right? So that's an automated way to create it. And at this point, the connections are not created. What they show up like is, you know, just these kinds of functional requirements. So create a rigid connection in those areas, right? So I have a mesh, okay, but I could, you know, very well go back in there and refine it, let's say 6 millimeters. And what I'd like is my connections to automatically update, my bolted connections to update. And you see here there's an update requirement, and you'll see that at this point, if I hide those, okay, and look at my 3D elements, you look at, you know, so it's been searching for all the elements that have been created around them. And why am I using this? Or why am I doing this, right? When I'm going to run my topology optimization, what I'm essentially doing is I'm trimming material from the body up to a point where I minimize the mass. But I need to keep the material where I have connections, right? So this is why I'm doing this. Okay. So that's my mesh, all right? So from a structural standpoint or from a topology optimization standpoint, what do I need to define? I need to define material. So material are defined here as titanium, but we also have like a full library of material already available in the software, but you can also leverage or point to a library that's used within the company. So you can use what we call a site library or a user material library, where you can import material and just leverage them across the different simulations. Now, in terms of what else, here, you know, just for completeness, so that bracket will be constrained at the bottom, so fixed. Imagine a bracket tied to a launcher or something of the sort. So that's rigidly connected at the bottom using our 1D connection tools. So again, that creates an associative connections between points. Okay, so in this case, I'm creating an associative connection between my functional points where my bolts are in a point in space, which I'll be fixing. And obviously I need some kind of, you know, maybe something a bit more complex. So what I've added is a simple lump mass here at the top, which I can simply create using our 0D mesh capabilities, create a mass of any, you know, in this case I think it's 350 grams of weight. Okay. So this is the first part. Okay, so this is the much that I've created. I've only meshed it, created some connection. And from a topology optimization standpoint, that's all I need to define in terms of meshes from a structural perspective. The next step is to create a simulation. And in SimCenter 3D, you know, the process of going from simulation to FEM is kind of seamless. Okay, so all we have to do is create a new simulation directly from that FEM, identify your weapon of choice. So in this case, I've been talking about structure, topology optimization. So that's our SimCenter Nastran solver. So a solver that came back from the 1980s, that was developed originally by NASA, but that's now been, you know, one of it was an open code. So it's been purchased by Siemens and then continuously developed, and, you know, until today still developed with 2 releases a year, adding further and further capabilities. Here, just a quick summary. Structure, we can do acoustics and vibroacoustics. Okay. Thermal flow or multiphysics for some of you guys if you do coupled analysis, thermal and structural. Okay. Now, the key here is that it is all the same environment. So even if you choose a different physics from Float to Nastran, you won't see a different UI. You won't need to export or put a new window in a different software. It's all seamless.
So if you to select answers, that would then use the answers solver.
Exactly.
To do number crunching.
Exactly.
You'd just be doing your pre-processing within it.
That's correct. So the UI within, you know, the UI for to apply the boundary conditions will be identical across the different solvers. Of course, if it's ANSYS, you'll have ANSYS-specific semantics for connections, for boundary conditions. The UI will adapt, but then under the hood, when you click launch, the only thing it's going to do is going to call the ANSYS solver.
So I mean, that's in my industry. We need to. There's the nuclear industry. There's an awful lot of checking and verification, proof of checking.
Okay.
But the easiest thing that for us to prove that is to actually see the input file. the input deck.
Okay.
So the INP for the Abacus hit, or the
Absolutely.
PDF for the master
Or the DAT file, yeah.
the deck file. Can we see that? Because I know some of these codes hide it.
Yeah, in this
Can
case,
actually see it.
yep, we can absolutely. Let me just show it right there. So you can see it at the FEM level without even anything from simulation inputted. So no case control for the subcases. But if you want, you can directly either preview it directly,
Exactly.
Here?
Yes.
or you can directly write it. So let me just create a solution. You can
Okay,
whenever you
that's
solve
fine. No, it's visible. That's the point. Yeah.
and write it.
Yeah, that's fine, because some of these hide it, and there's all sorts of horrors in there that you don't know about.
You never know what.
Auto SPCs, for example.
Yeah, so auto SPCs and auto MPC. Sometimes you never know what the behavior is going to be. Okay. So in terms of the solvers, you mentioned ANSYS, there's MSC, there's Abacus, there's LS Dyna. So actually, our office are in charge of writing those translators. So whatever you do in the UI, in the end, gets written to a file. So that's what we call the translating part. It's our office in our development team that takes charge of writing those. So if there's a capability missing, or any questions on how it's what it's writing, our team can be very nimble at addressing those questions. Okay, so I'm not sure if you've noticed here, but I'm now in a new environment. Okay, so that's the simulation environment. So it's pretty seamless. If there's any modifications that would need to be done to the mesh, all you have to do is go back here, and now you see the top ribbon here. So you can go back and edit the mesh, and everything is saved, so you can easily modify it. Okay, so that's how we walk seamlessly between the different levels. And the reason why we have this kind of different or stepping, if you wish, is to avoid or simplify the UI. Instead of having all of the functionalities and boom, everything in there, we just make it more simple and straightforward and user-friendly, for you to create simulations. All right, so my mesh is created. At this point, what I'm going to do is simply define a solution for topology optimization. So I'm going to create it here. Right, using our structural solver, we have a specific solution here. There's a bunch of stuff in there, but that's because I have a developer's license. But essentially, depending on your specific applications, we can only show what's relevant for your case. So we have star CCM co-simulation. So if you want to do FSI, so we have these portals available. We can do highly nonlinear simulations. But in this case, I'll stick to our topology optimization solution. Okay, and the reason for all of these is, again, to limit the input that you have to define. Okay. So create this, and then naturally for a topology optimization, you need to define, some sort of loading, some sort of criteria or objective. Okay, so that's what I'm going to do here at this point. So if you see here on the right-hand side, on the left-hand side in the tree, I'm going to call this topology. You have major objectives, what area you want to optimize, what kind of constraints, physical or physical constraints, or manufacturing constraints. When we have that talk about additive manufacturing, this is important if you have restrictions. But before I go ahead and define those, okay, what am I going to study on this bracket? What kind of geometry will I want to have? Well, I'm going to be exciting this geometry and subjecting it to 100 G loads in X. In the space application, because of takeoff, we'll want to have a minimum natural frequency. So I'll try to add that as a constraint as well. Some folks will want also to do random vibration analysis, have a certain PSD input for that bracket to respect. So we can do all of this in topology optimization. Okay, so how do we do this? Well, the first step here, this is a static subcase that I've created by default. So when it's going to run topology optimization, it will run this guy. So we'll apply, let's say, a fixed constraint to that point. So this is my to the ground, grounding. I'm going to apply an acceleration load. Say, on the whole model, let's say 100 Gs. We could apply 100 Gs in all directions, or in all directions at the same time, or one after the other. Okay, so it depends. Typically, it will be one after the other in the aerospace industry. Okay, then you can apply global scale factor. So I'm just going to do a simple one. Okay, that's my setup for the static analysis. So 100 G in X acceleration, try to find a topology that respects what. Okay, so objective, we'll create one. So our global objective here, is to minimize compliance across all the subcase. So in other words, maximize the stiffness of it, subject to mass. Okay, so typically in topology optimization, although the main objective is to minimize the mass, the way the problem is formulated for efficient calculation is minimize the compliance subject to target mass, and then we iterate on that mass, reduce the mass as we go. Okay, so that's a typical workflow for topology optimization from a mathematical standpoint. So in this case, that's it. Our objective is created. In terms of design constraints, we want a total weight of a maximum of, let's say, 500 grams, including the lump mass that it's connected to. So I want a bracket that's less than 150 grams. That's what it means. Okay. So that's it, constraint defined. We have our bolted connections. So the question is, what what area do I want to work on or let the solver work on? So we can either do this or specify which area you want to keep. So we want to keep that area containing the rigids, which is our structural connections. So that's why I've created that group beforehand. Okay, so give it a label. So I'm going to call this bolt. Bolt. Okay, and then we can define manufacturing constraints if we'd like. So in this case, we could ask for a bracket that's symmetric. Well, let's define that. Okay, so it's pretty easy to use. So we'll pick, let's say, point right in between this and this.
Often in these generative design and topology optimizations, it creates shapes which are probably suitable for additive manufacturing, but not suitable for, for example, injection molding.
Mm-hmm.
Is there anything that you can put in the manufacturing constraints, such as a wall thickness or a draft angle, or is that?
Yeah. So in NX, we have two levels of topology optimization. One is the designer, the analyst topology optimization, which is the one I'm showing you, which is mostly focused on structural analysis.
Mm-hmm.
Okay, so all the Nastran subcases or the random vibration, modal, frequency, static, nonlinear can be taken into account.
Mm-hmm.
There is a migration but however the manufacturing constraints available are somewhat limited.
Mm-hmm.
So in this case, we do have some angles. So additive manufacturing, you can look at the maximum overhang angle, for instance. You can also look at the casting die direction. So those we can take into account.
Yeah.
But we have another module that's called designer topology optimization. That's less focused on simulation. So the excitation that you can put is quite simple. It's static analysis or modal analysis. But then it has more kind of a manufacturer's intuition in it. But the idea right now, in the product roadmap that Joe had shown, is to integrate those kind of more manufacturer intuition constraints into this guy here.
Okay.
But we do have we do have some interesting manufacturing constraints that we can leverage.
Very good.
So I did create my symmetrical manufacturing constraint. I can also have another one where I want my minimum member size to be at least a certain size. I don't want very, very thin arms that are irrelevant from a functional perspective. So I can do this, let's say 10 millimeter. Okay, so these manufacturing constraints. And technically, I'm done, right?
At the moment you're going to run this for G's acceleration and stuff like that. Can you run it for different types of load scenarios, like thermal loads?
Yes, so using NX Nastran, we have temperature, we can apply heat loads in the Nastran model. We can apply different kinds. All the load that you typically see in a SimCenter Nastran solution, you can apply here. Okay. Now I'm only showing as static subcases, but in just a moment I'll show the different subcases that we can apply. One thing I'd like to add here is in terms of design constraints, I forget. Here the constraint is, I don't want any stresses higher than a particular value, either yield or 50% of yield and so on. So what we can do is apply that constraints on von Mises stress for all of the elements. So I'm just going to pick the mesh. So no constraints higher than, in that case, 245 megapascal, which is about 75% of the yield. Okay. So we can apply that constraint. Right? Now before I run it, let me just go ahead and look at the different subcases we can put. Right? So we're minimizing the compliance for all of the subcases, and those subcases can be statics, a direct frequency, if you have kind of an impulse, or a PSD that you can convert into a time, into the time domain. But we can also do modal frequency. So solution 111 in Simpson and Nastran to apply a PSD directly. Okay. We can also have a buckling step, and more right now we're adding more subcases available. So all the subcases you've seen when I looked at the solution, those are gradually being mapped into the product. But now, for now, what we'll do is we'll just apply a typical, first frequency limitation on it. So I'm extracting the natural modes, and having a constraint that the first mode needs to be at least 175 Hertz. All right. So at this point, we can run the solution, and the solver will take into account all the different steps you've achieved. We'll write all the information into a DAT file that you can review afterwards. And with a refined mesh, what I end up with is, oops, that's stealing the punchline here. Again, where's my geometry? There you go. Okay, so we can look at some normalized density plots. So under the hood, what topology optimization does, right, it reduces the density of the elements, right, and seeing how much material you can trim off your original part to get that bracket for space applications. This view is not particularly useful, right, because you see how you have all the elements and you don't get much out of it. What we do have is a dedicated post-processing module for topology optimization. Right, and now what you see here, this is starting to look like a bracket that can be 3D printed, right? So we can also refine it a little bit more to reduce the quantity of materials. Let me just bring that up here, right? So as we go, we can increase the amount of material we want to trim off and generate a geometry based on what you see here. Okay, so some folks will want to, remove as much material as they can, so increase that slider to the right, and then use that geometry. But others, right, will want to keep more material, and then use this as a template to redesign on top of it. Okay, using the convergent topology, convergent technology I've been mentioning during the presentation, and I'll show some of it shortly. Okay, but the important message is, this is not a dead end. This is the start. Okay, so what can I do at this point? I could create what we call a verification solution. So what this means is, at this point, I don't know what's the stress distribution on the part, right? All I have is a map of the elements that's been kept. What we can do is we can create a verification solution that will only keep those elements and run the subcases we've asked it to run, right? So it will run.
Is that not smooth? So essentially it's tape meshing the facets.
In that case, for that verification solution, because it's preliminary and it's quick, there's no smoothing yet. Smoothing can come in a further step, which I'll show shortly. But what happens with this one here is it's recreating a subcase or a solution with only the relevant element. And again, at this time, not smoothed, so the validity of the results you'll get is questionable because they're sharp ends, but it'll give you an idea of what's the weight.
That's always the difficulty, is where do you set your density level?
Exactly, yes.
That's always the difficulty with this.
Mm-hmm. We do have best practices that we've used a lot with our aerospace customers, but definitely I agree with you. It is always a challenge. Do we keep less and smoothen it, or do we take more and then trim it ourselves, right? So in this case, this will be the element where that will be used to rerun the solution. As you can see, the connections are still there, and all you have to do is run the solution again. But what you can also do, instead of just having a quick verification solution, is to export that geometry into an STL format. STL format is typically a format used for, it's a cloud of points or used for 3D printing or additive manufacturing. And that cloud of point can be used to work, we can work with it directly. Where's my geometry here? This is what the geometry looks like when it's exported to STL. Okay, so you do have some level of smoothing. It is still rough, but the question is, right, is what can we do with this geometry, right? Can we smooth it up a little bit? Okay. So in most tools at this point, this is a dead end. Okay, we can't do anything with this. It's visually appealing, but we can't fix it, or we need to export it somewhere else, and then mesh it somewhere else. And not even think about doing more simulation on it. But with our tool, when we have that geometry at the CAD level, which is the part level I've been referring to at the beginning, we can do a few things. So here what I'm seeing is that the face set is kind of broken. There's a kind of distorted face set. That's the natural thing that can happen when you do STL. We have automatic cleanup tools that can fix this. But if we look at the kind of things we can do, it's quite impressive. So I can use a brush, right? I can delete those face sets by just brushing over that area, right? So this creates a hole, right? So my geometry here is not a B-rep surface; it's a face set geometry, right? So it's full of face sets that we can play with. Now I can fill that hole by automatically detecting all the open holes in our body, just selecting it and closing it up. Okay, so now that part is closed, and now I do have a full solid body that I can work with. I can smooth it, right? So I can use some level of smoothing onto it. So I'm going to use just this face set here. Again, I could smooth it locally, but I can also smooth it from a complete model standpoint. So here it's selecting.
So this polygon modeling set of skills within NX, this is a separate module, isn't it? Or
It's still in the CAD. So it's a separate module in terms of the product structure, but in essence, we've not moved away from our typical CAD that you're familiar with. It's still the same environment.
So I did some reverse engineering recently, and you scan something, and then you bring it in, and you get left with an STL, which is in most cases a dead end. So then I have to take it into some other software, do all these operations, the polygon modeling, the smoothing, then export it as like a stat out, and then bring that in, and then surface over it. And it's the surfacing over it to get the A-class data.
Yeah. Which kind of map a cage on all this and
that's
get
the
that
really
B-rep surface.
time-consuming and difficult part.
In this case, you don't have to go outside now.
Yeah.
You can directly import it, and see we have kind of a smoothed geometry. Now there's a lot that can be done, so I won't go into the nitty-gritty details, but we have all the tools available now that you're used to, like all the extrude, the synchronous modeling tools to add geometry, to create holes. But we can also use our NX Realize Shape tool to create those A-class surface or B-rep surface around it that are parameterizable, right? Because sometimes you want to kind of maybe do optimization or parameterize your surface modeling around this. So you can still do it. Before I move forward, let me just show you one more thing that you can accomplish using this. So if I go back in my polygon modeling environment, at this point, as I've mentioned, this is one large surface. It's a face-set model. If I want to create features on it, I need faces. I need physical B-rep surface on it. So what I can do is use kind of these tools to split my face-set geometry kind of quickly. Right? So you see this, what is used to be one surface is now a defined face on which you can apply boundary conditions, create a sketch, create a hole in it. Right? So I can either do it automatically like this. So here I can pick 2, right? Or again, I can use a brush to just paint over it. So if I look at this area here, it's a bit more complicated. I can take my brush and just paint a surface on it. I'm literally creating a new face on it.
What if you wanted to create like a split line or a horizontal plane in the section of the geometry? Is there a tool for that as well?
Yeah, actually, I'm going to do something similar. I'm going to create a lattice meshing. Okay, sometimes when you do additive manufacturing, you want to take away some material and create a lattice geometry on it, to lightweight the part. So let's do this. Okay, so I'm going to go back here and use actually the NX Realize shape I've been talking about, right? So I'm just going to create a quick plane. That plane is going to be, let's say, in that area. Right? Now I'm going to create a what we call a cage polyline. Okay, so I'm going to take that plane I've just created. Okay, do a closed loop, and then just orient myself and create, let's say, something. Let's say I'm going to do something like this. So I'm going to try to remove material along that area and create a lattice mesh in it. Okay, so my cage polyline is there. So I can simply extract the cage this direction. Take this again, pull it in that direction here. Right, so I'm essentially creating new geometry on top of my facet geometry. So I'm going to close this so it becomes a body. Okay. Okay. So now I'm working with something called a subdivision body, which is done using B-Rep modeling tools like NX Realize Shape. So I can play, I can create geometry with these kind of shapes. I'm working with facet geometry, which is this. Can I work with parasolid-based geometry now? So I'm going to create, let's say, an intersection between this and this. Okay. So see. So now, if you see, my geometry is now split using that kind of weird shaped elliptic tube. And then what I can do is create lattice mesh in those areas. Oops. Okay. So I can take that zone here and create, different kinds of lattices that are suitable for lightweighting parts. They are typical in the additive manufacturing industry. So, what do we want today? Let's say tri-diametral, for instance. Let's take this one here. We can define we can specify a few dimensions. And excuse me, I just want to pick the right shape to make the full effect. So 4 millimeters, let's say a raw diameter of 0.5. Okay, create this, and now automatically it created all those features automatically. Okay, so this is kind of an automated workflow to create lattices, which is associative. And then the last part is to subtract. One second. Is to remove the original material, and you'll see that what I'm left is a nice and smooth lattice meshing on top of a convergent molding body. See the lattices? So these are, so from a visual standpoint, you still see kind of the edges, but as soon as we'll go into an additive environment, an additive manufacturing environment or on a structural environment, you'll see that these get converted in the right format. And you'll see what I mean in just a second. So that's just a snippet of it, right? There's plenty we can do. We can create new arms. We can redesign over the geometry. We can create holes. There's plenty of things we can do. One thing I want to show you is, assume you have that geometry and that you're satisfied with how it looks, right? Can you go back and before printing it, can you go back and validate the new behavior from a structural standpoint using all the solutions we're familiar with, EMAG, CFD, and so on, right? So how do we do this? Well, I mean, most of the time, most people would say it's not possible. Right? Well, what we can do is follow the same identical workflow, create a Nastran solution, maybe another topology optimization on it. Who knows? And then what you end up with is a geometry that's meshable, but also that converted those lattice into the appropriate element. So lattices, they're very thin. You don't want to model them using 3D elements, right? The value add of simulating those are limited. So what the solver does for you, or what NX does for you, is convert those into beam elements up front, right? And if we look at this, right, they do have the right cross-section and the right material that you've defined when creating the lattice mesh at the CAD level. Okay. Now another challenge, and actually I don't think there's any good tools in the market except ours that can do this, is meshing a convergent body is not easy. It's not easy because it's essentially one big facet. So, you know, when every mesher algorithm will try to look for edges to create those elements, and because there's no edges in that model, it won't be able to mesh. Okay, we do have a tool that's designed just for that. It's called 2D Mesh from Facets, and it allows you to mesh these kinds of body automatically. Okay, so I think the line here was 6.7.9. So what it does under the hood is it splits your polygon facets into, you know, subdivisions, create the edges, and then create the 2D meshes on top of it. And it will create a watertight mesh, of course. Let's give it a second. There we go. Okay, so this is what you get. You get a 2D mesh on top of your kind of organic geometry, which is not an easy feat to do. Okay, now that's 2D. If you want to create a 2D mesh out of it, you just extract the 3D mesh, so solid from shell, from what you just created. Okay, and there you go. You have a 3D model with the lattice mesh connected to it.
Is the lattice mesh represented by 3D modeling techniques?
So the lattice,
Still 2D.
yes, so the lattice mesh are represented using 1D beam elements.
Mm-hmm.
So it's you know, it's essentially a 1D connection element
Yeah.
with a cross section that's tied and spidered, if you wish, connected to the 3D model.
But if you wanted to, say for example, STL this out now to 3D print it, okay, does it need to go through another conversion process? And would that convert into a nice clean STL?
So if you want to go directly to additive manufacturing, you wouldn't even go to the FEM level.
Mm-hmm.
You'd stay. So let me go back to my original CAD. So you'd go from there,
Yeah.
and directly open the application for additive manufacturing, which will take into account those.
Okay.
So let's see if I have it here. You would go directly in that environment.
Yes.
Okay, so you wouldn't have to go. It would not represent that beam for 1Ds because that's only for FEA purposes, right?
Right. Okay.
Mm-hmm. That's kind of the idea where, you know, the solution is at, right? Allows you to really do an end-to-end workflow from functional requirements to analysis, topology optimization, bring back the geometry to the CAD for designers to, you know, either wrap something around it or use it directly to do some, you know, add some features to it, and then allows a pipeline to simulation again. So I've rerun you know, I could rerun a structural solution, but I could run a thermal analysis in this case with that organic geometry. Any questions so far?
In some other, you know, like in additive manufacturing now, metal 3D printing is quite a big hype, and including these lattice meshes inside metal parts is really common. But as the technology advances, you can go smaller and smaller with the lattices.
Mm-hmm.
It's quite difficult for the STLs to represent that without the file becoming huge or the computation power. And some of the other software programs out there have got a new type of format for representing the STLs. I think it's .arch.
RCH.
But I've not tried it, but apparently it represents using this 1D method.
Okay, and just keeps the data as metadata to that 1D.
Yeah, I just wondered, because when these models get quite big, you know, like you can see them, you try to mesh it, and it takes a long time, and then the models it can slow down the computer quite considerably, and make things hard to work with.
It's something to actually, Nick, do you know if Joe Luxmore is still there?
He's gone.
He's going, okay. That person would have known the answer. The
Yeah.
RCH format is supported.
Yeah, I'm not working with it at the moment, but I just tried to do something like this the other day, and the model just, I've got quite a fast computer and everything slowed down when I put lattice on it, and it crashed, I just gave up.
Taken to this extreme, if you like, I mean, you could represent that lattice region with a smeared prompted region of solids.
You could, yeah. So you could have
You know,
did.
so that's probably what that is the lattice gets smaller and smaller
Yeah.
and smaller, and effectively calculating equivalent solid properties.
Yeah.
It'll just look like a solid,
Yeah.
but it won't be as stiff as a solid. And it might have orthotropic properties depending on which one the lattice is facing.
What I was trying to do was like an aerofoil with a solid skin on the outside, and then just fill it full of a lattice, and then have variables, a different type of lattice running through the core to create stiffness.
Yeah.
And then, yeah, but, like I said, it all crashed and fell over.
But back in the old days, you would probably have smeared properties.
Right. Okay.
So you would choose your, you'd probably put composite properties into your socket, depending on effectively what the equivalent properties of the lattice would be, which, as I say, might be different in tension as well as shear and torsion.
Okay.
So that, and that will become more valid as your lattice gets smaller and smaller, because it would act more like a smeared, different material.
Okay.
But quite how you'd make that, because the information to fabricate it.
That's it. I think that I was reading that when you try to export that information to fabricate it, it's so huge that the 3D printer is going to take a long time every time it has to process the layer. And there's a new format that somebody was talking about at a different company, but I don't think that's mainstream yet. But I can see it becoming a bigger problem as we go more and more into this type of design and optimization and lattice structures.
I think from a structural integrity modelling analysis point of view, if your lattice is small, don't try and chase it. The individual elements in your lattice. When it gets small enough that you can reasonably understand its properties by an equivalent modulus.
Yeah.
From a
shear
simulation
moduli,
standpoint.
Pascals, then you can go with that if you're a structural analysis. But how you will make that, I don't.
I see. Yeah. Okay.
If you've got a large model, because again, we're using ANSYS, so we're going out of the NX environment into ANSYS, and then solving on a high-performance computer, because it's taking several hours to solve.
Using the ANSYS software.
Using effectively a separate machine, then you can't use this. You can't effectively use that as a connection, can you?
So whatever's in the so the solution to 100 topology optimization uses a SimCenter Nastran solver, right? Now the output the output result that you'll get from ANSYS, you can always import it back in SimCenter 3D. So if you have the mesh, so let me just open it here real quick. So there you go. So in ANSYS, let's say you do a topology optimization in ANSYS and you get a result. As long as you can export that result into a neutral format, you can always bring it back up in SimCenter 3D. Okay. Now the question is, let's say you remesh that geometry, can you export it back to ANSYS afterwards? Yes, you can. Yes, you can also reuse the ANSYS solver afterwards on that same mesh once you've imported it back in SimCenter 3D. But the key here is the export of that resulting organic geometry from the ANSYS solver. Does that address the question?
I think, I guess I'm not quite sure how it would work.
I think you might just have to handball it. You might have to export the file carried over, and then carry the results back, and then you could resume. Unless there's some way of linking to a machine.
We've always treated it as like two separate processes. You take it out, you work on it independently, and then you bring it back in.
The obvious thing to do with that is go to the cloud if you can.
Yeah.
And then submit source on the cloud. That might be the way around. I'm not nothing to do with these guys, but potentially that might be the way around. I'm sure we'll see how we go through it.
Excellent. All right. So if you give me just 2 minutes for now, unless you have any questions for this, I'm going to just set up the other models for another SimCenter demo. So in this case, what I'll do is I'll show associative modeling from CAD to simulation back to CAD, just to show how a design change can directly be updated or reflected at the simulation level. And then the other demo will focus on AimSim and STAR co-simulation.